Alright, so we're going to take a real quick review here in 5.1. If you remember at the beginning of the year, we did a bunch of property of exponents rules. So if you take a quick read through, I want you to look at each of the different rules that we've talked about, such as product of powers, where if you have the same base and they're multiplied, you add the exponents, power of power, you multiply, and so on and so forth. And we're just going to take a real quick travel through to practice some exponent rules with just things that look maybe like this bottom one or with scientific notation. Alright, so we're going to take a quick trip through example 1 here. We've got like bases multiplied, so when they multiply we add the exponents, so I'm going to have 3 raised to the 5 plus negative 2, so that's 3 to the 3rd power, which is 27. The second one, we have a power of a power, so we multiply, which gives me 2 to the 6th, or 64. And here we're going to treat this as a negative 5 to the 1st power. Okay, so again, we have, just like part A, like bases multiplied. And so I'm going to add the exponents. So I've got 1 plus 3, which is negative 5 to the 4. So negative 5 times itself 4 times is a positive number, so I'm going to get out positive 625. And last but not least, we've got a fraction inside, so I'm going to carry the exponent to both. Okay, so I've got 6 to the negative 3rd over 5 to the negative 3rd, because we're going to treat those as if they were both inside raised to the 1st power, so I multiplied negative 3 times 1. And then since the exponents are negative, like what we have up here, wherever it is, if it's in the top, it moves to the bottom. If it's in the bottom, we move to the top. So that's going to basically flip-flop this and become 5 to the 3rd over 6 to the 3rd, or 125 over 216. Okay. So how might we see this in scientific notation? Now, hopefully in science classes you remember scientific notation is a way that we deal with either really, really tiny numbers or really, really big numbers. So this A value is a number, it can be a decimal, between 1 and 10. So for example, 3.25 times 10. Now if I raise it to a positive number, like the 6th power, that means I would move and times this number by 10 to the 6th. So I move the decimal place 6 places to the right. If it were a negative 6, I would go the opposite way and move it 6 places to the left. Either way, any open spaces we fill in with a 0. So, just so that we can read, the population of the United States is 3.2 times 10 to the 8th. So I would mean move the decimal place 8 places to the right and add zeros in. And it says if each person pays approximately 8.2 times 10 to the 3rd power in dollars in taxes annually, find the total budget for the United States government for 1 year. So I'm going to take, if this represents the population, how many people I have, and this is how much money each person pays, I'm going to multiply these two numbers to find out how much money the government has for us here. Alright, so how am I going to do that? So I'm going to look for the like pieces and multiply them. So I'm going to multiply these two numbers together, and then I'm going to multiply these two numbers together. So let's see, my 3.2 times 8.2 is going to give me 26.24. And when I multiply 10 to the 3rd times 10 to the 8th, and I add the exponents, I get 10 to the 11th. Now I would think that I was done, however, this right here does not follow the initial condition here that we said for scientific notation. This number must be a number between 1 and 10. So what I'm going to do, in order to force it to do that, I'm going to move the decimal place 1 more over, so that I have this, and then I have to change my exponent accordingly. So now I got to decide, since I only moved it 1, does this become a 12 or does it become a 10? So the way I know is if I'm moving it farther away from the direction that the decimal place would move or closer. In this case, I'm moving it farther away because I would have to move it to the right. So I'm going to add 1 and make this a 12. Okay, so then this would be dollars, how much money the government has for the budget per person. Okay, so a light year is the distance a particle travels if it was moving at the speed of light for an entire year. And so we know the speed of light is 3.0 times 10 to the 8th power meters per second. So how many meters are in a light year? So the first thing I need to do is figure out, since this is meters per second, and I want just meters, I need to know how many seconds are in an entire year if this particle is moving for an entire year. So I'm going to take 60 seconds, because I know that's how many seconds are in 1 minute, okay? And I'm going to convert this all the way until I get how many seconds are in a year. All right, so then let's see, I know that 60 minutes are in 1 hour. Now notice I'm alternating which side so that the units cancel. Okay, so now I have 1 hour. There are 24 hours in 1 day. There's 365 days in 1 year. Okay, so now what I see is my hours canceled, my days have canceled, so I have this seconds per year, and that's what I want. So now when I multiply all of that out, I get 31536,000 seconds per year. And to put that into scientific notation, I'm going to move the decimal 1, 2, 3, 4, 5, 6, 7 places. So I've got 3.1536 times 10 to the 7th power. All right, so that's how many seconds are in 1 year. So I'm going to multiply that then by the speed of light so that I can figure out how many meters that is. So I've got 3.0 times 10 to the 8th power times 3.1536 times 10 to the 7th. And just like the above, I'm going to multiply the like pieces. So the 10 to the 8th and 10 to the 7th, and the 3.0 and the 3.1536. So when I multiply the two pieces together, I get 9.459 for this piece, times, and then I add the exponents, 10 to the 15th. Now this number is satisfactory, so I don't actually have to move any decimal places like I did before. So this would be meters and how far it's traveling. Okay, so back to a little more advanced stuff here, advanced practice. Okay, so like example 1, I have 3 like bases, so I'm going to add all the exponents together. So I get a to the 4 plus 6 is 10, plus negative 3 is 7. So I get a to the 7th. Here, I'm going to carry the exponent outside through, and I have to multiply the exponents, then anything that is negative I'll move. So I'm going to have w to the 9th, because negative 3 times negative 3 is 9, over z to the negative 12th power. All right, so since I have a negative in the denominator but a positive in the numerator, I'm going to leave the w to the 9th in the numerator and just move the z up to join it. So I'm going to have w to the 9th, z to the 12th. And technically it's over 1, but you don't have to write it. So once the z moved, there's nothing left down there, so it's like being over 1. All right, so now we've got a bunch of stuff to do here. So first thing, using order of operations, I'm going to do the parentheses first. So I'm going to leave the numerator alone for now. And I've got an x, and then I've got 3y squared. So that means I'm going to square the 3 and the y. So that's going to give me 3 squared is 9, and y squared. So now I can simplify all the like pieces. I've got the 27 over 9, which is 3. I've got x to the 3rd over x, gives me x squared. I've got y to the 4th over y squared, which is y squared, because we subtract the exponents. And then I've got a z to the negative 2. There are no z's in the denominator, and it's a negative exponent, so I'm going to move it to the bottom. And that would be my simplified. And last but not least, we've got very similar to C. So what I want you to do, you're going to have a little bubble pop up here, and I want you to try this one. Okay, try simplifying it and see what you get, and match it with what you think is the correct answer.